Good day. So it's a little bit of an odd topic. It does have to do with optics, it's a little bit standard. But I will link it to plotting here because we did some interesting experiments a long time ago that are related to this topic. Causality and kind of strong. One of the corny jokes that I try to make. It's about the refractive index. One of the take-home messages was based that the refractive index is kind of the one property to rule them all. So there's the ring in one. If you know the refractive index, you can calculate basically all optical properties. So jump into the conclusion. Okay. So briefly, I will talk about what's causality. Small recap of the electromagnetic properties. Show you the derivation of the relations. I think it's fun to show it. It's very mathematical. I think it's nice if you've seen it once, you might have to reproduce it. It's nice to see, and then a few examples. So what is going to be? So what's going to be the bottom line? The bottom line is that going to be that causality dictates that the real emission part of the physical response function are related. They're not related in the sense that they information is expressed in the so-called Causality equations, dispersion relations. And applied to optics, that means that we can derive Causality equations for the refractive index. You have to make one assumption there, that is an assumption that you always make. Maybe that there is some weak interaction between the light and matter. Furthermore, the imaginary part of the refractive index is a complex quantity, and the imaginary part of that complex refractive index is related to the absorption part, which means that we can express this Causality relation as a relation between the real part of the refractive index and the absorption. That last relation is the one that is practical point. So this is how it will look like. What you see here on the left hand side is the familiar absorption coefficients from hemoglobin and oxyhemoglobin, so substance that is inside the red blood cells. See that, of course, that there is a difference between the oxygenated and deoxygenated form. Through these kinds of bonus relations, we calculate how the real part of the refractive index will look like. So on the same wavelength scale, visible wavelengths you see for both compounds. How it looks like. Of course, a couple of things, because it is a true relation, it's a functional form. That means that if this is different between the two compounds, then this is going to be different as well between the two compounds. What you also see is that some distinct features, like here these absorption peaks, and if you look at the oxyhemoglobin part, the two absorption peaks are pretty close here, they translate into features in the spectrum of the refractive index. These two peaks here show last thing what you see in this graph is these data points. So what we will do, and as you will see, if we do the transformation on this data, we will get this shape, but not the exact height. So we need a measurement in order to scale it to the right. So the points that you see here are very accurate calibration measurements. So causality, as stated by Galileo, basically the effect cannot precede the cause. If you kick a ball, it does not roll before. So that has been still the way that people have looked at it, of course. But later on, the 20th century, a lot of thinking went on about the implications of this causality, also in terms of the uncertainty principle. It's all discussions that we're going to skip now. But what it is funny is that so in the 20th century, this is a conference in 1929. This is how conferences looked back then, and there's kind of a famous attendance here. You see Niels Bohr, for example, is in the audience. Erevest, Casimir, Pauli, Darwin. It is not Charles Darwin, but his nephew. But still. En Kramers and Krook, the guys who the equations of this is them. So how do we go about describing response functions? Well, very simple. We have a response to a physical system that is given by the input and some function that connects the causal function. What you see here from this integral is that the response at time t is basically a weighted form of everything that happened before. So the response can be instantaneous, that the integral short, but it can also be an input that lasts for some time. So this is then the function of function. This is the function that describes the system, the causal function set of t, and we can write that. So there's a time domain function to the closed state Fourier transform, and then write it to the frequency domain. The benefit of using the frequency domain is that we can write this complex function, which makes the math a little bit more versatile.
Is this also some kind of convolution?
It is by definition a convolution because it is a function multiplied by time shifted other function and they're integrated. So that is a convolution indeed. Do we have a correct feeling for what this function describes? So why it is just in time? I think you can imagine it's just a kick and the ball stuff on it. But for do you also have a feeling what the frequency domain representation means? Give you an example.
In terms of this?
No, not of the ball, but of
just in general.
Just in general, yeah. So, for example, if you have let's have a physical system like this, resistor and capacitor here, and I'll put the voltage here, and I'll measure the voltage in here. Measure voltage out over here. So this is a physical system which has an input and will have a response. The response will be dictated by the value of this resistor and this capacitor. If I would, if I did a time domain picture, let's say I would apply time domain sinusoidal. So voltage and sinusoidally varying voltage. What do you think that the output is going to be?
I think I can guess. Isn't this some kind of low pass filter? The capacitance. So it depends a bit on the frequency of this sinusoid, but then it might be attenuated.
Yeah. So basically, what we'll see is that if this again is a sinusoid, this is low pass filter. Assume that it's a little bit attenuated. It can also be a little bit of a phase shift. So it's going to be a sinusoid that's a little bit less than amplitude. So this would be then the response in the time domain of one frequency. As you said, the response will depend a little bit on the frequency of the input. So if you plot the output response as a function of the frequency, this being a low pass filter will look like will look something like this. So the slow varying sinusoid will be just passed through and disturbed, and the frequency of the sinusoid is higher. So that is what this frequency response just means. So it does have a physical. Okay. Now again, for these causal functions, the time domain of the frequency domain, there is this relation between the real and imaginary part of that function. And then because this, I'm just joking, because this exists for the complex refractive index, and we use the complex refractive index for scattering properties and also for absorption properties, it's truly. Thanks. last time that I promise. So very brief recap to Maxwell's equations. Of course, these need to know if we try to solve that, combine it in a single second order differential equation. Solve that using the usual methods, just trying signs and cosines. Then we'll find that the solution, one solution is traveling wave in space and in time. It's the wavelength and the speed of light. Once we can write this as a complex exponential with an amplitude and phase that we already saw as well. And by substituting this expression in the equation itself, we can solve for C1 and C2, C1 proportionality constants. Will have to be. So the properties that carry over that appear in this equation is first of all the speed of light, or the speed of the wave. In a material, what we can do is write that in terms of vacuum values, subscript 0, relative values that are specific with certain materials. They will change if you take a different material. And that means that we can express the speed of light in a material as the speed of light in vacuum. So that is the million 3 times 10 to the power 8 meters per second, divided by a constant m, which is then related to the material properties. And the constant m is the refractive index. This is where it originated from. We start with the next situations. And again, the important thing to remember always is that all these properties are dependent on frequencies. So basically dependent on the color of the light that you use here. So m is a function of lambda, of k, or omega, whatever you like. You like to express it. And in this case, it's also a complex quantity. Let's skip this one. So if you look at the solution, the plane wave solution, traveling in the k direction in complex form, then it's written here with refractive index appearing just before the wave number, and this refractive index is complex. So we write it as a real part, as an abstract part. So quick question is, what is then the final? If you make substitution, what is the final expression for the electric field, and what is the final expression for the density?
Intensity would just be actually.
Expression for the E field is just found by substitution of this complex number into the complex exponential. Something's happening there. So the thing is, what happens is, so this is pure. So E is outside of the axis here. So this is a purely complex exponential. So if we now put in this substitute this new complex number, then this E and this E are going to cancel out. So all of a sudden we have an exponential that has both the imaginary part and the real part in the electric field already. Of course, if we calculate the intensity, we have to square the electric field or multiply this complex function. Then the other E will also drop out, but the real part that we already have is squared. So and basically this is then so by substitution we get this. So we have an oscillation term that still remains there. That only depends on the real part of the refractive index. And we get this purely real part, this real exponential decay of damping that contains the imaginary of the electric field. So what this is now is a traveling wave still, but one that is exponentially damped as it travels along. That's what the imaginary part is. then taking the square of the field, so to obtain the intensity, we get that this oscillation part comes out as well. Only the exponential decay part survives because of this taking the square we now have a factor of 2 there. This you can recognize this is just yet again another form of Beer's law, and the Beer's law, a decaying exponential. So that means that we can identify this 2k times kappa, 2k times the imaginary part, we can identify it as the absorption coefficient. So propagated beam, propagated light beam is damped with this Beer kind of exponential minus 2 times. So there's a direct. So this is immediately following from the definition basically of the refractive index as a complex quantity. That the imaginary part that is related to the absorption coefficient. So that means that we can take all these absorption coefficients that we know, so this is, for example, water, and can immediately convert that into imaginary parts of reflective index, if you like. It is just a scaling factor with lambda or with k or with omega, whichever scale we're looking at. All right. Back to causality. So that means an optical response, response to an electric field as the input. In the material will be the electric displacement. So we will get the displacement of charges in the material. The causality that dictates that this displacement cannot, that is the response cannot be faster than the speed of light. And the result, and that is then what we'll see again, is that because of causality, the real and imaginary parts of the refractive index are related. And that also means that these two phenomena that are depicted here, so on this side is this refraction of different colors by prism, that is due to the shape of the prism and the real part of the refractive index. On the other hand, if you sit behind the glass, you don't get a sunburn because the UV light that causes sunburn is absorbed by that same glass. So this glass can be of the same material, and both of these effects are essentially related through this stroke. This is the functional form that will be divided. So the real part of the reflective index is given by the absorption coefficient, which was proportional to the imaginary part of the refractive index. This is expressed in terms of frequency now, so omegas. A couple of things to note here. Let's immediately show you that it's not that straightforward. The first is that if you want to know the refractive index at only one frequency and wavelength, you would need to know the absorption coefficient over all other frequencies. This interval runs from 0 to infinity. So that immediately tells you that that's going to be different because we don't have access to it. We can measure absorption coefficients, but certainly not from wavelengths from 0 to infinity. So that is another problem is that this denominator can blow up. If your omega is by coincidence the same as the prime, then the whole thing goes to infinity. But that is a mathematical problem. And that mathematical problem is solved through this by writing this p in front of the integral. What this essentially means is so-called Cauchy principal value. What it essentially means is that you integrate right up to the discontinuity and stop, briefly look the other way, and then continue.
Elegant.
Very elegant. Sometimes math is really
right.
It's really cheating. Yeah. Okay, trust me on that screen. So let's look at let's look at the math. Yeah, and again, I just want to show you this because I think it's fun. And if you learn, that's your bad one. And you don't have to reproduce it. See how it goes and see how much cheating is going on in here. And that's so we started out with this causal function z of t that describes the response to some input. So this is some kind of input, and you have a response that can lag a little bit longer than the input and the duration of the input, it will not start. So the first thing that we can write in is that Causality requires that the response function f of t 0 for t is less than 0. Also, we expressed it as this convolutional form. So response is given by the input at all times prior to the times that we're looking at. First thing, like we said, it's convolution. If we take the Fourier transform of both sides, this R of t simply becomes R of omega, and the Fourier transform of convolution is equal to the product of the Fourier transforms that are inside the Fourier rules. So that means that this convolution in the time domain is simply a product in the frequency domain. Z of omega is the Fourier transform of Z of t, and E of omega is the Fourier transform of I of t. Z of t is a real function, describes a real response of system, but the Fourier transform itself, the Fourier transform, that can be complex. So we write Z of omega as having a real part and the imaginary part. It also holds for R and E functions. They are real in the time domain, but if you take the Fourier transform, they will be complex. Okay. First trick. This is what holds for all these response functions. First, it is real. It is Z of t 0 for t less than 0. There's no response before the input. And eventually, if the input stops, it will go to sleep. So it means that it's integrable. There's an area in that. It also means that Z of t will not change its shape if we multiply it with a step function, the Heaviside step function. So that is defined as follows: h of t is 0 for t is less than 0, and it's 1 for all values of t that are larger than 0. It's basically just step function. So if we multiply Z of t with this function, basically nothing changes. That also means that if these two are the same, that their Fourier transforms must also be the same. The Fourier transform of Z of t is equal to the product to the Fourier transform of this product. The Fourier transform of Z of t is written here for the definition. So Z of t multiplied with the complex exponential and then integrated. Now we use the same trick, the convolution trick again. The product in the time domain corresponds to convolution in the frequency domain. It's the same rule, but then the other way around. So that means that the Fourier transform of this product can be expressed as the convolution of the two Fourier transforms. Or slightly more palatable way, that means we take Z of t, multiply it with time shifted version of the frequency shifted version, I should say, with of h of t and integrate from minus infinity to infinity. These were the same. These were the same. These. But let's first try to work out this interval. We can look up. You can just look up Wikipedia. The Fourier transform of the Heaviside function that is given by this form. It's a really strange form. So the real part is in delta p. The delta p. The imaginary part is 1 of the scales with 1 of the frequency. So we can still substitute that into the integral. So we get z on the prime times this part here, that part here, also now because it's this convolution also shifted in frequency.
The Fourier transform of the Heaviside step function, basically because it's just a sort of 0 Hz peak, which gets a sort of DC offset, I guess.
Yeah. I didn't.
Would make sense.
I guess. So this part is delta function. So we can split this into two integrals basically. This integral minus an interval. The delta function within an integral just selects the argument. So if an integral is an area on your curve, if you multiply the function with only one delta peak and then calculate the area, you just select the value. So this will just select the value here. The other part will then take this. We'll take this integral. And now we're almost there. Because the Fourier transform of z of t was equal to the Fourier transform of z of t multiplied with the Heaviside function. Now with this manipulation in place, we have that on the left hand side we have z of omega. On the right hand side, we have half z of omega minus some leftover integral. So we can bring this part to the other side. And end up with this complex integral for the response function. So this is the frequency, the main form of the response function of omega, and we see here that we can express it as an integral of itself, basically. So this function so by itself, this is some kind of mathematical magic. But not really useful. That comes when we split z of omega into real and imaginary parts. Z is 6% times. So there we go. It's an eigen here also an integral that because of this complex number in front here, carry that over, fill in as well. So we get two terms on the right hand side, one imaginary part and one real part, which we also have on the left hand side, one imaginary part and real. If you now equate the reals and imaginary parts, then we're getting closer to what we wanted. So then we see that we can express the real part of the Fourier transform of the response function as an integral of the imaginary part of that function, and vice versa. The imaginary part is expressed as an integral. So we're now getting closer. So remember, we were working towards the refractive index, the real part and the imaginary part of the refractive index. This already kind of shows where this is going. If this is the real part of the refractive index, and this is the imaginary. So these are called the dispersion relations, and this is still completely general. This holds for any response function. It holds for this RC circuit on the board, and it holds for the refractive index. It holds for any kind of system. Again, caveat here is that if you now it's even a little bit worse than I said before. If you want to know the value of one frequency, you would have to know the values of I at frequencies from minus infinity to infinity. So think through math. Even though the math is straightforward, the practical consequences are quite staggering. No such thing as fifth negative frequencies in physical world. So that we have to solve first. You can know that by making use of the fact that z of t is a real valued function. So z of t uses that means if z is a real function, that means that it's Fourier transform z of omega is an even complex function. We already saw an example of this. Do you remember the spectrum in OCT? That is a real valued function. If we then take the Fourier transform, we get two copies of the signal, positive and negative, because that's yeah. So that means in this case that an even complex function has z of omega is z equal to its complex conjugate again with the sign of omega first. Z prime on the reverse. So if you expand this into the imaginary part for Z on the left hand side, of x conjugate is x plus EI, so it becomes of x plus EI becomes x minus EI on that. If you change the signs. So for this complex, for this even complex function, we have these relations: x of omega for the real part, x of omega equals x minus omega, y minus omega equals minus y omega. So we'll use these. We can use these a little bit later. So to get rid of this, these negative frequencies, what we'll do is split the integral into two parts. So one part that runs from minus infinity to 0, and the other part that runs from 0 to infinity. And we'll leave this part alone. So we want to try to manipulate our way out of this part. So the first step we can do is swap the integration boundaries. Swap here from 0 to minus infinity. Now running the other way around. We have to put a minus sign in front of the integral. So step number 1. Step number 2 is to change the sign on omega squared. So here, 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 and here. And then the last step is use this even conditions property, which again makes this plus and this. From this expression, we can now, because the integration boundary is now both from 0 to infinity, we put into a single integral. Take I out of the square brackets here. These the terms that we can cross multiply. So within the brackets to rearrange these omega terms, that you see this. And finally, my regrouping. The result is this: x of omega now as an integral running from 0 to infinity frequencies with a changed denominator. So first, when we started out, we had the integral which ran from minus infinity to infinity, and we had 1 over omega scaling in the denominator, and now we have omega. Which at least means that we've tricked our way out of the negative frequencies. We can do the same approach for the imaginary part, and I'm going to go very quickly here because I suspect that there is a typo on the slide somewhere. So I'm not going to spell out every step, but you can do that for yourself if you like. This is correct, at least. So for the imaginary part, we get a similar expression. It looks a little bit different because omega is now outside of the form. It's not otherwise it's kind of like same. Okay. The conclusion. We have the results. We have this causal function. It's a real value. It's square integrable. Then the result is that Z of omega Fourier transform is an even complex function. And then the real and imaginary parts of that complex function are related through these dispersion relations. Again, we still did nothing system specific here, so this is still completely general for any response function. Still, the problem being that in order to know the value at 1 omega only, we still need to know the conjugate part of okay, there's one small problem, small caveat that when we get complex reflected index itself is not a response. There is not an input that you multiply with the reflected index and then get them. So it's not a response function itself, but it is related to response functions. And that means that the properties of the Gauss curve and the dispersion relations carry over to the reflective index, but it is itself not a response function. We can relate it to the reflective index to the susceptibility of the material that basically tells us displacement of the electrons when it's illuminated by here you can see that the susceptibility is a response function. The incident electric field multiplied with susceptibility gives us the polarization density, so the density of the separation of electrons in the material. So this one oscillates, then this distribution also oscillates, and there is a frequency dependency. This susceptibility here tells you how strong the response is going to be for different frequencies, for different colors. So susceptibility is a response function, and that means that the comes down directly can be applied for that. Now, this susceptibility is kind of a wild walk through all these electromagnetic properties from a few slides ago. Susceptibility is related to the permittivity simply by the R-1. The permittivity is related to the refractive index. So the refractive index is the square root of the relative permittivity. Which means that if we assume that the response is really, really weak, we can write. So we can first write the refractive index in terms of this susceptibility, for which the Gauss-Jones relations existed. But if the response is weak, then we can tailor ourselves out of this square root, approximated as 1 plus a half times susceptibility. So now it means that if this has a Gauss-Jones relation, this is simply scaling an offset, this will have a Gauss-Jones relation as well. So the real part of the refractive index is then approximated by 1 plus a half times the real part of susceptibility. The imaginary part is half times the imaginary part of susceptibility. And this is then the dispersion relation for the real part, substituting ourselves this expression for the real part of the refractive index, and then finally rearranging and writing in terms of the absorption coefficients. So we have the kappa of the imaginary part is related to the absorption coefficients. So we can finally group all these terms together. And finally, with this equation. So there we go. The real part of the refractive index is the function of the absorption coefficient. Same thing. The imaginary part. So for 10 years, the absorption coefficient can be written as an integral function. Real part of the refractive index. Okay. There's this one loose end, and that loose end is the blowing up of the denominator. And as I told you before, it's simply inserting Cauchy's principal value. So it's a trick still, but even tricks you can write semi-importantly so that they look really sophisticated. Taking limits and putting them into the integration boundaries. And all of a sudden, it's still cheating, but it looks much more fanciful. So it really is just integrating up until that point. Stopping. We'll take that for what it is. So finally, to write this formally, we put P in here that just simply tells us, it's not a constant, it just tells us, okay, we know that this blows up, we take it into account. Yeah, and the volumes. Okay. So let's see what the consequences are. To calculate then the real, so let's investigate how this integral, how this equation works. We have a spectrum. We have a spectrum of the absorption coefficient. We have U of A, and let's assume that it looks like this. So there's just one single absorption peak at some normalized frequency here. So it's 1. And now the question is if I would calculate this integral, how would then the real part what you see is that we have to multiply it. We multiply the spectrum with function 1 over omega squared, which can be shifted. And then the integral tells us that we calculate the area under the product. So for each, basically for each frequency, we shift this omega squared function to the frequency and calculate the area under the product. So for this case, so let's say we want to calculate it at a frequency that is less than the resonance frequency. So here's the absorption peak at ratio is 1, and we want to calculate it. So this is, because the scale is a really zoomed in version of that function. So we multiply it and calculate the area under the curves. This function is completely symmetrical. So if we place it here and calculate the areas, then we will get a small contribution from this area, negative contribution, and a larger positive contribution from this part of this area. So that means that adding both means that we get a higher value of the refractive index. If we move it to the other way, to the other side, if we evaluate that frequency that's higher than the resonance frequency, it's simply the other way around. So this part of the function selects an area negative contribution that's large, and this part of the function selects a smaller positive contribution. So that means that we'll get a low value of the refractive index. And if it's up, and of course if it is in the middle, see then is that the contributions negative side are the same as the contributions there, so it is to 0. So here we get higher values of the refractive index, here we get lower values of the refractive index, and here we get essentially 0. Well, not 0. So if we would keep doing that, then the shape would look something like this. And, frequencies left from resonance, we get positive values exactly at resonance. It would be 0, and then after that we get lower values. So this absorption peak here, the spectrum translates into an oscillation in the real part. That is the effect of this. So this would be on a frequency axis. So again, around this peak, we get an oscillation. If you would plot it as on the wavelength axis, which is more common in the absorption coefficients and refractive indexes in optics, then of course you have to account for the fact that this is 1 over the wavelength is proportional to 1 over frequency, so it gets a little bit stretched, and so that you still see the oscillation. All of a sudden, Wikipedia had this animation. That's how it works. Well, that's also a little bit flat. Okay. If you look then at glass again, so glass has a huge absorption peak in the UV part of the spectrum. So here you see a transmission as a function of the wavelength. So transmission is really low here, which means that the absorption is really high there. So the absorption spectrum of glass essentially can the absorption spectrum then something like this, the UV. And then if you would calculate this value for this real part of the refractive index, you would have this oscillation just around at the UV peak. So here you would have this substring and then like this shape going forward. So this is then the UV part, but if you look at the visible part, absorption of glass is of course pretty low because you can look through it. And then the real refractive index has this decaying shape. That of course corresponds to measurement as well. This is just the refractive index of glass as it is measured. And because this is decaying, because it is this function of wavelength is decaying, you get this effect in the prism that you can separate these different colors. So one quick question for you, if you can see if this landed a little bit. Can you now let's say we take this absorption spectrum, so it has a small absorption peak here and a huge absorption peak there. So obviously this one as well. If this is the absorption spectrum, or this now let's make it easier, if this is the imaginary part of the refractive index, can I predict how qualitatively predict how the spectrum for the real part will look like? So rule of, not sure why since we're playing this at the time. So you get around an absorption peak, you get an oscillation in the real part of the spectrum. So around these two peaks, there will be an oscillation. This peak is higher, so the oscillation will be stronger around this peak. And the oscillation on an omega axis has the shape that it first goes down. First goes up and then goes down. So on the omega axis, it will be a short oscillation going up, then down, and then here going up, crossing at the peak, and then yeah, I have some. I think I have some stuff. Yeah. So it's better to see for this huge peak. So the oscillation is going up and then going down, and then going up again. This one has the same form. It's superimposed on it because this peak is shallower. That also means that but in principle, it is just a superposition. So you get the same effect around each peak, and then you add them in the same.
What's this last? The third.
Different. Oh, that is really perfectly aligned. That is really perfectly aligned. So this is still kind of straightforward to do. This one is a little bit. If you want to do it the other way around, it's a little bit more complicated. So let's say the real part looks like this, and we want to guess how the absorption spectrum, of course, the absorption spectrum looks like it corresponds to this. So here we have two oscillations, and we have a trend that goes downward in the long run. So how many absorption peaks do we expect in this? Because we have this one oscillation here and one oscillation there. So this would lead to two absorption peaks. Which one is higher? Second one, because this is stronger. And then this trend, that's then the tricky part, because the trend is going down, just like with the bars, that suggests a little bit that there is a huge absorption peak somewhere over here as well. That caused an oscillation in the spectrum as well, that we're now here riding on the tail of that guy. Well, software is right. So this is still the same. This was for the other one. So this is on frequency scanning. This is on the measurement scale.
It's a very quick question. So when you asked like what does it look like, I was like this little bump, which turned out to be correct. Either way here, through more of like an axial oscillation. which actually sounded more like what you said, like an oscillation. But I guess it doesn't really go down as much because the kappa is still rising, like it doesn't really return to the zero value. Yeah, why it's not like full oscillation.
And here, of course, this is on an omega axis. If you go to 1 over omega axis, the whole thing flips. So now the big absorption peak appears as an oscillation here. The smaller one appears here. So looking at it on the left-hand axis makes it. Okay, this is then the one for how I expect that the absorption coefficient would look like. So we have an oscillation somewhere around here and an oscillation somewhere around here. So I would guess that there is an absorption peak here and an absorption peak here. Because this oscillation is stronger, I expect this one to be stronger than this one. And because the trend is negative, it could suggest that there is a huge peak.
Maybe it's a stupid question, but when we know when the attenuation is first up on the
I think it's because it's the lab data instead of the relative.
Yeah. So
I was just thinking the same thing.
Yeah. So on the lambda scale, it goes first goes down and then goes up, and on the frequency, it's the other way around. Yeah. Yeah. So that's a bit tricky. That's. Okay. I have a few more slides, so I suggest we just go on. There is still this problem that you would need to know absorption coefficient over all frequencies to answer the single frequency, which is of course not the case. So what we can do is that if we have some kind of measurement, we can use that we can still do the transformation, but because we do it on a finite range instead of from 0 to infinity, we don't get the exact value. So we get the shape, but not the exact offset. So we can do a calibration measurement, some measurement at some frequency, and then use it. I'm not going to ask you to do that. I will show you. The trick is called a subtractive Armstrong relation. So we take this relation, and we're going to subtract the known value of the measurement. Trick is that for that part, you can also write this dispersion relation. It's simply a question of matter of writing down the integral part with omega 0 instead of omega. Now you have two rules that you can combine into a single term, and then again a bunch of omegas that you have to cross multiply to get out there. So let's do this then. And finally, the expression becomes this. So n of omega is now we have an offset point from the calibration. And then a slightly more complicated integral part of omega and of two omega squared terms and of still this looks this looks like a complication, but it's actually beneficial because now one benefit is that we have an actual measurement to the scaling, so we can scale it to the right. And the other one is that this function which we multiplied now becomes sharper. So this one this shape, because we have two terms now, it becomes squared, and we square it becomes more narrow. You remember that what this thing did is we set it at a certain frequency and then multiplied it with the spectrum and calculated the area. If this one is broader, then you take into account more of the original spectrum. If this one becomes narrower, the value was determined by a smaller part of the spectrum. So it becomes less important that you're missing data in the edges. It simply becomes more reliable to center. This is there, so it's now scaled with omega to the fourth power, which is much new. And of course, this is really great because now you can if you can now do two measurements. For example, then you have 2 points to scale your spectrum with, and you get additional terms in the denominator here, so it even becomes more narrow. So the more data that you actually know that you can put in, the better your estimation is going to be.
I don't quite see why it would be more narrow in the sense that we've got omega and we've got omega 0. But if those are equal, I can see why it gets more narrow, but they aren't necessarily, right?
Yeah, because now because it scales with omega prime squared, and that is the one that is the one.
Yeah, but I was thinking like the sort of place where you get the explosion. Also, another sort of related question is we've got the P, which in first case was to get rid of the when omega equals omega prime. Now we've also got omega 0 equals omega prime, which would also make it.
Yeah, but the P was just saying, okay, we notice this and we take it into account. So P just counts for every possible blow up. Okay, so maybe no mistake is that I drew it. If you plot it, you can see it a little bit easier that it's actually a narrower function that slides along. Okay, so now let's look at the consequences that we have for water and for plants. So roughly speaking, the large absorption peak of UV and all water has that, glass has that as well. What causes the real part of the refractive index to decrease with wavelength in the visible parts, which is like this one. So that is true for water, it's true for glass. As a rule of thumb, the real part of the refractive index decreases with wavelength in the visible parts. Of course, because that already accounts for about 70% of absorption of tissue because of the high water content. It also accounts for this is these are calculations again. So this is the refractive index spectrum of water from wavelengths from 10 nanometers to 10 meters. And then this small niche here is the visible part of the this being the imaginary part of the refractive index, which was related to the absorption coefficient. Indeed, shows here that there is this huge absorption in the UV part of the spectrum. Then the absorption drops, so does the imaginary part. The visible part, you can see through water, we know that. And then if we go through to higher wavelengths, you get the absorption of the places. So if you then do the calculation, the integral to calculate the real part, we get this graph here. We see not that very clear, of course, because of the scale here, but you see this. You see an oscillation, a small oscillation here around this huge P. Very subtly, you can see that it decays in the visible part. So you can zoom in a little bit on the real part. We can zoom a little bit in on the real part of the refractive index and the visible wavelengths, and you see this decay. What's also funny is that it is, the real part from measurement is found to be temperature dependent. So what does that imply for the absorption coefficient? Also temperature, that also has to be temperature dependent. Relations with both ways. So if there's a difference here between different temperatures, then it has to be a difference in absorption. So that is also something that is experimentally found. For blood, for oxygenated and deoxygenated hemoglobin, then this one I showed you in the beginning, where all this basically comes together. This is the absorption coefficient. From the absorption coefficient, you can calculate the imaginary part of the refractive index. That do the Kramer-Stronach calculation. You get the real part, the curves, and then using one measurement point, you can scale them to the correct values. So this is only over a short wavelength range. here is over a somewhat larger wavelength range. So what is interesting here is that we did calculations for oxygenated and deoxygenated blood here for hemoglobin and for plasma. So if you have these two values, then you have all the input you need to calculate scattering properties of a red blood cell. You need the refractive index of what is inside the red blood cell, that's this, and the refractive index of the medium, that is in the case of blood plasma. This is nice. This is a measurement. So measurements of the refractive index are notoriously difficult. It's very hard to do. These are very subtle changes, and just because of the way that you have to arrange the experiment, there's a lot of things that can go wrong in terms of offsets or scaling with a lot of calibrations. So getting a reliable measurement of refractive index is really difficult, and that is also the reason why we only have these two data points here to scale, because it is just too difficult to do it. This group, Friebel, they did it. So they measured the refractive index, the real part of the refractive index. If you, what you notice if you compare it to these calculations, there are some good things and there are some bad things.
It sort of shifts. Yeah, there's some offset.
Yeah.
And lower the frequency. Yeah, it's the main peak they sort of get, but then around 250, it's way off.
So the good thing is this oscillation here that is also shown. That is also visible. So that is what we expect. So what's maybe not a good thing is that there is indeed an offset, but that can be due to simply having a different measurement. So I'm not going to say who is right or who is wrong. I mean, we could use here as well. So then when we have to scale up our measurements, or he could be wrong here, and we have to scale it down. The interesting part is what happens here. So here in the measurement, you see that his refractive index goes way up, while in our calculation, I think we are wrong here, because this is really the effect of having only data over a limited range. So even though we use this subtractive time-square relation, which should minimize edge effects, still here we are missing data. So doing the analysis here will lead to something. So the result for our measurement is that it is kind of flat here. I think that is the missing data. So here I trust this more. So as you can see, this is data from 2005. That's already quite a long time ago. In the meantime, the experiments on doing refractive index measurements have become better. So nowadays there is more data available that also verify that this is actually correct. Or not complete. This is my attempt. This is me in 2005. From a sadly departed pig. So we work with that. No, I can explain. I'll explain it. So we work.
I can explain it.
I can explain it. I have an alibi. You know, we work in the hospital, and in the hospital they train surgeons. And at some point, these surgeons really have in their training, you have to operate on with humans, right? So they operate on pigs. So what we do is when we want to use some blood for an experiment, we say, okay, just let us know when you're going to do that. And again, at the end of the day, can we, when the pig is, let's say, operated, can we have a little bit of a few liters of that blood? That is how we get to it. So what I tried to do here is have this blood in a circulation. This device here is a blood oxygenator. So they use it in the operating room to oxygenize. So if a patient is operated and they have to bypass the blood flow, bypass the lungs, then we use this machine to keep the blood saturated. So we included that in our experiment. So we were circulating blood here over an optical table. keeping nice control of the oxidation when at some point the fuse is one of the tubes disconnected, and then it turned out that the pump that we used was actually pretty strong, which was probably the reason the thing broke in the first place. So that experiment ended in me covered in pig blood. Of course, so this is why you have to wear a lab coat.
What a compensate to
Yeah, that was 2005. Things are different. Things are different back then. Yeah, the annoying part was that I had to go back at the train, which was fine. When I had the coat, but yeah, let's say that this part was a little bit more suggestive. Anyhow, that's why we want to do the count. So that's at that point I decided, okay, I'm not going to do the measurements anymore. I'm just going to do the calculations. You know that this refractive index goes into the calculations for scattering properties. Scattering properties of blood, just like the refractive index, are very difficult to measure. I'll explain in the next lecture even more why measuring the scattering properties are so difficult. But this gives us a kind of a way of this is easy to do. You can break red blood cells, you can put them in a nice, safe setup where things do not blow up, and you can measure the absorption coefficient and then fire this complicated route. You can calculate the scattering properties. That's for next time. Real and imaginary parts are related. That comes to relations. The refractive index is not a strict response function. We can derive Armstrong relations. So that stability is weak, which is something that we'll assume all the time. The imaginary part is related to the absorption coefficient, so the Armstrong relation in this case is expressed as real part as a function of absorption coefficient, and that gave us because we don't know the absorption coefficient from -infinity to infinity. We use subtractive Kramer-Stokes relations to have a little to leave that a little bit, so we can use it on smaller spectrum as a rule of thumb. Remember, if you have a large absorption peak of UV, blood, water, glass, then we will have decreasing real part of the refractive index. If you remember that rule of thumb, you know that there's a lot of math behind it. This is why. Okay, that's my message today. So go work on the assignment and have a good weekend.
tomorrow.
No, I kind of wanted to go, but then I saved it for another time because I think after this lecture, I guess the official ending.